Okay, bulk properties of materials. It's one of the most descriptive parts of the course, so it's quite hard that people find a lot of it. However, some phrases and some keywords are quite straightforward. So it's those that we're going to concentrate in this section, but it's building up to this idea of understanding how the different properties, which although they're based on mathematics, for the stuff that we're going to do is more descriptive. So it's more like generic kind of phrasing. So we're going to look at various things including stiffness and strength and so on, but there's also Young's modulus, density and all those other key phrases that come in. So section 4, bulk properties of materials. For most of this it's to do with the graph, okay, and how the graph links to what's happening in materials. So we'll come back down to that at the moment and just pick up on some key terms from GCSE. So for us, most of the time is where we're doing the maths. Okay, so I'm just going to put in here that this is the maths. Now, for that, you could be talking about Hooke's law, so we could do in force and extension, or we could be talking about Young's modulus, which is coming up at the end of this chapter, which is a similar thing but for materials. Now for the bulk properties, the bit that matters the most, as I say, is the bit where the maths happens, so that is going to be the elastic section. So when you've got deformation going on, when it's deforming, what you have got is this section that we're on. This is the linear section, okay? However, you'll get to a point where you no longer, for what we do, use the maths. Now, don't get confused by this. All we're going for here is basically the limit of the straight section. So for us, it's that proportionality that is important, which means that when it stops being proportional, at GCSE you might call it directly proportional, but to us it's just proportional because they all are a straight line, if we're saying that, and all go through the origin. So when we get to the end of that straight section, if we look at our graph here, that's here. It's got nothing specific to do with the properties of the material. It's what's happening is something slightly changing inside, but it doesn't change the behavior. It's just the end of where we can do the maths. So for us, that's going to be our P on our graph. Okay, so that's the key bit that matters. However, when we go beyond, there is a big gap for, because I forgot to change the brake, so there's nothing missing from here. But when we go beyond that point, you'll get to the elastic limit. Now, some materials are brittle, and so the elastic limit might be the point at which they break. Okay, but the elastic limit is where you load it and unload the material, and it still goes back to its original length. It's still behaving elastically. Sometimes, just to give you a kind of pick in there, and I'm going to put in brackets, is that it's also the yield point. Okay, so inside it's not going to go back. Now, depending on the shape of the curve, you get different yield points, so I'm going to stick that in brackets. But for us that we've got on here, this is going to be our capital E on our graph down here. Okay, now in something like this, the yield can be very, very different. In some things, you might get a real kink, so it kicks up and then it drops right down, just like in the PowerPoint that I've shared. So the yield is where the structure within the material is changing. Okay, so that's a more material word. But for us, we're looking at the graph, so elastic limit is a better description. Beyond that, anything that you take off, if you go up to that point and then you take off the stress, so reduce the stress, then the strain will also go back down. It will go backwards as it goes down, so it will follow a pattern back. But you've got this section here, and this bit will be your permanent deformation. So that's the bit that you don't want for most things. If we're thinking about, for example, a cable on a lift, you don't want it to permanently deform. It'll still be well within the safety limit. Yeah, okay, so it's nowhere near the ultimate tensile stress, the biggest value of stress, but then the floors on the lift won't line up with the floors on the floor itself, so you'll get that depth. So you don't want to go into any permanent deformation with a lift cable, for example. So when it is not behaving like, like elastic, then the word we use is plastic behavior, okay, or plastic deformation. Again, it sounds posh and you can use it, but if you put plastic behavior, that's fine, but it's not plastic, okay, it's not a polymer, but it's behaving plastically. Okay, so again, still extend, but the length is, the extension is not proportional to the stress that's causing it. Okay, so some materials do not do it. That's materials such as this, but we'll come back to that in the next section. So what is actually happening on here? Well, this is the point of what is happening at Y. Okay, so here is our yield point. Sorry, I forgot to label that up there. Let me just put it in there. So if we're looking at Y, this is what you see actually happening. You'll actually see a physical change in the behavior, and it is what's known in the trade as, necking, because strange enough, it looks like a neck. So at this point here, you're getting this necking. Here, obviously fracture. Okay, so again, it's not breaking. Try and use technical language. Fracture is the point that we're after there. Okay, so nice short sharp section, but those are all key terms that you're going to need when you're doing your work on this. Okay, thanks very much guys. Keep it simple with that.